Hello students, welcome to this module, which is the third in the series of modules on differential equations. In this module we'll continue with the theme that we started off in the previous module, that is how do we solve linear differential equations. Okay, the key is of course linear. Okay, using the method that we call the method of eigenfunction expansions. Okay, so we'll call it the method of eigenfunction expansion. Okay, this is also called, or some textbooks call it, the finite Fourier transform. Or you might be familiar with this in some form from your earlier exposure to partial differential equations. This is also called sometimes the method of separation of variables, or rather what we usually call the method of separation of variables to solve partial differential equations is basically related to the method of eigenfunction expansions or finite Fourier transforms. Okay, so while these are in general valid for both ODEs and PDEs, the way separation of variables is normally introduced to us in our earlier courses is as though it is applicable only for PDEs. Okay, now the fact that you are going to use eigenfunctions, okay, that is, the key idea is that suppose you have a differential equation of the form Lu is equal to F, where this is known and this is a linear differential operator. This is a known function. L is a linear differential operator. Okay, and U is the unknown function that you are interested in solving. Okay, so the key idea in the method of eigenfunction expansion is as follows. You would like to expand the unknown function. Just for the sake of simplicity, I'm indicating it as a function of single variable x. Of course it can be function of many variables as well. So you would like to expand this as some coefficients ci times phi of x, where this phi's are the eigenfunctions of the operator L. Okay, so that is, you solve this problem, Li phi of x is lambda I phi I, then if you are guaranteed to have orthonormal eigenfunctions, okay, then the idea is to substitute this back in this differential equation and solve for these coefficients of expansion, okay, directly from the differential equation. We'll see how this can be done. Now, in order to understand this, in order to make sure that this method always works, you need a set of orthonormal eigenfunctions in which you can expand your unknown function u of x, right? So you require a set of orthonormal eigenfunctions. Okay, now from our earlier experience on and discussion based on matrix operators or operators, linear operators in finite dimensional spaces, we know that Hermitian matrices are guaranteed to have real eigenvalues, and the eigenvectors corresponding to distinct eigenvalues are orthogonal, which can be made orthonormal by simply using a convenient normalization. Okay, so basic idea is that if you have a Hermitian matrix, the solution of its eigenvalue problem guarantees a set of orthogonal eigenvectors. Okay. Now, what is the analog in differential operators in function spaces? Okay. The analog of Hermitian matrices, remember, also are self-adjoint matrices, in the sense that if A is equal to A dagger, okay, and A dagger is the same as A star, which is the adjoint, okay, if A is A dagger, then such matrices are Hermitian, okay, or self-adjoint. Now we are interested in finding out the analogous case for differential operators. Okay, so first of all, we want to know the conditions under which a differential, when is a differential operator. When I say differential, I always of course restrict myself to linear differential operators. When is a linear differential operator self-adjoint? Okay, that's the first question. Of course, a differential operator L is self-adjoint if it's equal to its adjoint. Okay, so how do you define adjoint? The adjoint of a differential operator is defined using inner products in a manner very similar to how we define adjoint of a matrix. So if you have a function V and then differential operator L operating on function U, and if you can write this as the inner product of L adjoint, which is denoted as L dagger, V comma U. Okay, now this is the adjoint of L. Okay, L dagger is the adjoint of L. Now this is not all, because if you integrate by parts, this inner product is basically an integral. So if you integrate by parts the left side to bring it to a form that is close to the right side, then you will also get a bunch of terms that are evaluated at the boundaries. Okay, these are what I'll call boundary terms. Now these have to be, of course, satisfied by boundary conditions as dictated by the physical settings of the problem. Okay, these are dictated by boundary conditions, right? So basically we have to ensure that for an operator to be self-adjoint, L to be self-adjoint, L has to be equal to L dagger, and boundary terms should vanish. Okay, so these terms should go to 0. Okay, and the boundary conditions of the original and adjoint problem must be identical. Adjoint problems must be identical. It is not sufficient if you just have L is equal to L dagger. Okay, it's not sufficient if you have the differential operator L is the same as its adjoint. You must have, very importantly, the BCs of the original problem and the adjoint problem must be identical. So both this and this are important in order to for an operator L to be self-adjoint. Okay, so this is a very, very important notion, that for an operator L to be self-adjoint, okay, you need one, L is equal to L dagger, and by making the boundary terms vanish, okay, you arrive at the second condition, that is the boundary conditions of the original problem and the adjoint problem must be identical. Suppose if L is L dagger and the BCs of the original and adjoint problem are different problems, are different, then of course the operator is not self-adjoint. The differential operator is not defined based on itself, it is also intimately linked to the boundary conditions. Okay, so clearly if the second option is if L is not L dagger, again the operator is not self-adjoint. Okay, so in order for the operator to be self-adjoint, it has to be equal to its adjoint, and the boundary conditions of the operator should be identical to the boundary conditions of the adjoint operator. So these are the things that we have to keep in mind. Okay, so let's try to illustrate this with the help of some examples using some simple differential operator. Okay, let's consider L is minus d squared u by dx squared. Okay, and the boundary condition for this operator is given to us as u of 0 is 0, u of 1 is 0. So what do we have to do first? We have to first check whether we can write u comma lv as L dagger u comma v. This is the definition of adjoint problem plus boundary terms which will be made to vanish. Okay, because we have the flexibility of by choosing appropriate boundary conditions of the adjoint problem. Note that we only know the original the boundary conditions of the original operator L. We have the freedom of fixing the boundary conditions of the adjoint operator L dagger. So we make the boundary the boundary terms of this integration by parts vanish by choosing the appropriate boundary conditions of the adjoint problem. If L is L dagger and BC is equal to BC dagger, that is the original and adjoint problems have the same boundary conditions, only then L is self-adjoint. If L is self-adjoint, then its eigenvalue problem is guaranteed to have real eigenvalues and orthogonal eigenfunctions. Okay, so now I'm going to start with this inner product. So this inner product is nothing but 0 to 1, that's the domain. U occurs first, so in our convention that will occur with a complex conjugate. L is minus d squared by dx squared operating on v times dx. Okay, this is the left side. Now I'm going to integrate by parts. Okay, if I integrate this by parts, I'm going to consider this as u and this as dv. So I'll get uv. Okay, so I'll take the minus sign out. Minus integral v du, but there is already a minus sign, that minus and minus will cancel to give plus 0 to 1 v, okay, which is, and then du, which is this. Okay, again you do an integration by second integration by parts. This will give you minus uv. Now I have to integrate this by parts. I'll consider this as u, this as dv plus uv minus integral 0 to 1 v, which is simply v. Du is d squared u star by dx squared dx. Okay, now this is the left side. So what we have shown is integral 0 to 1 u star minus d squared v by dx squared is equal to these boundary terms plus I'm rewriting this as plus 0 to 1 v minus d squared u star, okay, by I can write the differential first, minus d squared u star by dx squared times v dx. Now let's look at the boundary terms. We are given the boundary condition that u of 0 is 0, u of 1 is 0. Okay. Now I'm going to look at the boundary terms, which are these two terms. Okay. I'm going to consider these two terms now. So this is nothing but minus u star 1 dv by dx 1 plus u star 0 dv by dx 0 plus du star by dx 1 v1 minus du star by dx 0 times v of 0. Now let's see which terms we can knock off to 0. We are given that u of 1 is 0. We are given that u of 0 is 0. Okay, but we have no idea about what these are. These are completely arbitrary. We cannot specify what the derivatives are because we have already specified the function values at the two boundaries. So we have the freedom of choosing these two conditions for the adjoint problem so that the boundary terms vanish, because the first two terms are anyway 0. So we'll say v of 1 is 0. That will make this term 0, and then we'll say v of 0 is 0. That will make this term 0. So the boundary terms vanish if v of 0 is 0 and v of 1 is 0. Okay, then we are left with, if we'll take a look at this equation, we are left with integral 0 to 1 u star lv is integral 0 to 1. Of course dx is there in case if I forget, right? Of course there is a dx here as well. This is nothing but L u star times v, okay, dx. Now the operators are identical, so this has to be L dagger, but then L dagger is the same as L, so the operator is self-adjoint because both this, okay, let me write this as L is L dagger, both this is satisfied and PCs are identical between the original and adjoint problems. Only then you are guaranteed to say that you have a self-adjoint operator. Okay, so now if instead let's take a second example, same operator, instead we'll consider boundary conditions u0 minus u1 is 0 and then u prime 1 is 0. Okay, now the operator remains the same, so we have to only look at the boundary terms. Okay, which is minus u star 1 dv by dx at 1 plus u star 0 dv by dx at 0 plus v of 1 du star by dx at 1 minus v at 0 du star by dx at 0. Now in this question or in this example we are told that u prime 1 is 0, that is this is 0, and we are told that u of 1 and u of 0 are identical. That's what this means. So we can pull out u of 1 or u of 0, and then you can write it as dv by dx at 0 minus dv by dx at 1. Then in addition, okay, we can also set, okay, we can just write it like this first. Okay, u of 0 is not given to be 0, and we cannot say what is dux by dx at x equal to 0. This is arbitrary. So in order for the boundary terms to be 0, we should demand that this is 0 and this is 0. Okay, now if we do that, we get boundary conditions that v prime of 1 is v prime of 0 and v of 0 is 0. Okay, so but these are not the same as the original boundary conditions. Okay, so the problem is not self-adjoint even though L is L dagger. Okay, the differential operator remains the same. Now we can generalize this notion to a more general second order operator. Suppose I consider a general second order operator, differential operator, which is a2 of x d squared u by dx squared plus a1 of x du by dx plus a0 of x u. Okay, then you can go through the integration by parts, and you will find that L dagger, the adjoint operator L dagger u, is d squared by dx squared of a2 star of x u of x minus d dx of a1 star of x u of x plus a0 star of x u of x. Okay, now we require L is equal to L dagger. Okay, so we require, suppose I expand this out, the differentials here. Okay, so L dagger u, so first I have to write this as d dx of a2 u, so I'll get a2 star du dx plus u da2 star by dx minus the same here a1 star du dx minus u da1 star by dx plus a0 star of x u of x. Now I again differentiate this once again. Sorry. So this is a2 star of x d squared u by dx squared, right, plus da2 star by dx du by dx plus, now if I do this, I'll get I take this constant and differentiate, I'll get the same thing again, so I can put a 2 plus u d squared a2 star by dx squared. Okay, now minus u da1 star by dx plus a0 plus u of x a0 star. Okay, this is L dagger u. Now if I want this to be the same as, if L dagger is the same as L, then we require, okay, sorry about this, L dagger. If then we require, what is L? L is simply this operator, a2 of x second derivative, a1 of x first derivative, and a0 is x times function. So if I take the second derivative, then I require, then if L is L dagger, then I will say that a2 of x must be a2 star of x first. Second, if I equate the first derivative, okay, what I'll have is yeah, I'm sorry, I forgot to write minus a1 star du dx, this term. Okay, so the first derivative will, if I equate between this and the first original problem, it will give me simply that 2, or rather a1 of x is 2 dA2 star by dx minus a1 star of x. Okay, and third, I'll get a0 of x is d squared a2 star by dx squared minus dA1 star by dx plus a0 star of x. Okay, now these are the three conditions. Let's assume the functions to be real. Okay, just for clarity and simplicity, ai of x is as real functions. Okay, then we simply have a2x is a2x, that is satisfied, the first condition here. Second condition is a1x is 2 dA2 dx minus a1 of x. If we take this a1 the other side, then I will get a1 of x, it's 2 a1 of x, and the 2 cancels out to give me dA2 dx. Okay, right? And similarly, if I use this a0, if it's real, a0 cancels, then a1 is simply dA2 by dx, so this is also trivially satisfied, automatically satisfied once you make this connection. Okay, so if these conditions are satisfied, then the operator is Hermitian. Okay, so Lu should be a2 of x d squared u by dx squared plus dA2 by dx du by dx. Okay, plus a0 of x. Instead of a1, I am writing dA2 by dx. Okay, so I can rewrite this as Lu is d dx of a2 of x du dx plus a0 of x u of x is 0. I'm sorry, there has to be a u of x here, obviously. Okay, right, so when I write this, then L becomes L dagger. Okay, of course you need the boundary conditions of the problem. Two problems should also be identical in order for the entire operator to be self-adjoint. Okay, so this is how one determines the adjoint problem. Okay, all right, so now before I go to the method of eigenfunction expansion, I'll note in passing that we had this Fredholm's solubility condition, if you remember, for Ax equal to b in terms of the adjoint solutions, adjoint homogeneous solutions. The same thing is valid for differential equations also. Okay, the same Fredholm's alternative or the Fredholm's solubility Okay, so let's say you want to solve LU is equal to F. Okay, A less than X less than B, and then some boundary conditions BIU is equal to gamma I. I goes from 1 to P. Let's consider the homogeneous problem just by setting F is 0 and gamma I is 0. Okay, and the adjoint problem, okay, with the adjoint boundary conditions. Okay, the Fredholm solubility is rather similar. If LUH is equal to 0, the homogeneous problem has only the trivial solution. Then LU is equal to F has unique solution. Okay, if LUH is equal to 0 has k linearly independent solution, the homogeneous problem, let's say if it has k linearly independent solutions, then LU is equal to F has a solution if and only if the inner product of the homogeneous solution to the adjoint problem is orthogonal to the forcing function. It's not orthogonal. The inner product should be equal to summation j is equal to 1 to P, okay, gamma j, which are the original boundary conditions, times B dagger 2P plus 1 minus j times VH I. Okay, now this is the solubility condition. Of course, if the boundary conditions are trivial, then this will become 0. The boundary conditions are homogeneous, then this will become 0. Then you simply have the forcing function to be orthogonal to the solutions to the homogeneous adjoint problem, which is exactly identical to what we saw in the case of matrices. Okay, now of all the second order operators, we just saw that this second order operator is Hermitian, and provided the boundary conditions are also same, of course, then the operator is Hermitian and self-adjoint and is guaranteed to have real eigenvalues and distinct eigenvectors. Now in the subject of mathematics, there is a special operator called Sturm-Liouville operator, which is defined as minus, very similar to what we just did, plus q of x. Okay, now this operator is very similar to what we just had here. So this operator can be self-adjoint if the boundary conditions of the original and adjoint operators are the same. Now consider an eigenvalue problem of the form, these are the eigenvalues, these are some functions that may be there in the problem. Okay, right, so then one can show that if the boundary conditions, if the boundary terms in this operation if I take the inner products and do the integration parts, after this, if this come out to be 0, okay, then the Sturm-Liouville operator is guaranteed to have orthogonal eigenfunctions because it's a self-adjoint operator. So the Sturm-Liouville operator is a very general form of a second order operator, and it is a self-adjoint operator which is guaranteed to give real eigenvalues, and eigenfunctions corresponding to distinct eigenvalues are orthogonal eigenfunctions. Okay, so this is one important idea that you should understand based on what we just discussed. This is a special type of a self-adjoint operator, which is always it's always second order differential operator, which is always self-adjoint. Now if I put p of x equal to 1 and q of x equal to 0 and rho to be 1, then I'll get the usual simple harmonic oscillator problem. Okay, and many other equations like the Bessel equation, Legendre equation, the Chebyshev equation, they can all be expressed in the Sturm-Liouville format, and therefore they are guaranteed to have orthogonal eigenfunctions provided the boundary terms vanish. Okay, so this is something that you always should keep in mind, that the boundary conditions should remain the same. Okay, so this is a very important idea, the notion of a Sturm-Liouville problem, because it helps us to generate, or it guarantees us that there will be some operators like the simple harmonic motion operator, the Bessel operator, the Legendre operator, the Chebyshev operator, and so on. Okay, they will always have orthogonal eigenfunctions corresponding to distinct eigenvalues, and therefore it will be much easier to solve problems or partial differential equations or ordinary differential equations, provided we have an operator that is in the Sturm-Liouville format. Okay, I'll stop here and I will continue from take it from here in the next module.